Hello, this is Caleb Pelagi from Cleveland State University presenting on an active audio crossover circuit for my honors project. As an electrical engineer, it is incredibly key that we cover the core concepts behind the operation of this circuit. If you do not understand the basics, it makes trying to understand this design very difficult. The impedance of a capacitor is measured in ohms and varies in response to frequency and the value of the component. All capacitors behave similarly. At low frequency, they behave as if they were an open circuit. At high frequency, they behave as if they were a short circuit. Another way of thinking about this is that at high frequencies, the signal can pass through the capacitor, and at low frequencies, the signal is blocked by the capacitor. Capacitors can be added to a circuit for one of two functions, coupling or decoupling. A coupling capacitor is in line with the signal, meaning that the signal can only pass through the capacitor. Coupling capacitors are used to filter out DC parts of a signal and function like a high-pass filter. A decoupling capacitor provides an alternative path for a signal, meaning that the signal can either pass to the output or pass through the capacitor. By attaching a decoupling capacitor to a line carrying a signal, high-frequency parts of a signal can be filtered out, as they will pass through the capacitor rather than to the output. This circuit functions like a low-pass filter. Using this knowledge, an engineer can look at most filter circuits and determine whether that circuit is a high-pass or a low-pass filter. A high-pass filter is a circuit that allows only high-frequency signals to pass from the input to the output without distortion. Low-frequency signals experience both a reduced gain and a phase shift. On the right, you can see a Bode plot of a high-pass filter. A bandpass filter is a circuit that allows only a specific range of frequencies to pass from the input to the output without distortion. This range of signals is known as the passband, or the bandwidth of the filter. If a signal is in the passband of the filter, it will experience no phase shift and will not have a reduced gain. If a signal is above or below the passband, the signal will experience a phase shift and reduced gain. On the right, you can see a Bode plot of a bandpass filter. This type of circuit is ideal for situations where very high frequencies and very low frequencies are not desired in the output signal. For this circuit, we need to separate the high and low frequency components of the input signal. The high frequency part of the input signal will be sent to the mid-range speaker. The low frequency components will be sent to the subwoofer. In order to isolate the high frequency parts of the audio signal and send them to a separate speaker, we need to make use of a high-pass filter. We can identify this circuit as a high-pass filter as it is coupling capacitors, which only allow high-frequency parts of the signal to pass to the amplifier. In order to isolate the low-frequency parts of the audio signal and send them to a subwoofer, we need to make use of a bandpass filter. Why a bandpass filter, you may ask? If we allowed DC components of the waveform to pass through the filter, the subwoofer would draw power from the filter, which can cause distortion. As mentioned in the previous slide, we want to ensure that the subwoofer is independent of the filter. In order to provide proper isolation, we added a voltage buffer to the output. This voltage buffer completely isolates the input from the output, which allows the subwoofer to be driven at a set voltage independent of the filter. After designing each of the independent circuits, we can combine them all to form the full audio crossover filter. The full schematic of this filter can be seen here. This is the breadboard of the circuit that I built. On the right, you can see the high pass filter and the output to the mid-range speaker. On the bottom, you can see the band pass filter and the voltage buffer. Here is what the input audio sounded like before passing through the audio crossover circuit. Notice Here's what the audio sounded like after passing through the high pass filter. Here is what the audio sounded like after passing through the bandpass filter and the voltage buffer. You might notice that the vocals sound incredibly distorted, while the bass line can be heard loud and clear. This is because the vocals lie outside of the pass band of the filter, so they experience both a reduced gain and a distortion factor due to the phase shift. Thank you for listening to this presentation. If you have any questions about the circuit or would like to see the schematic, feel free to ask Dr. Dong. You might notice that the audio is not only louder than in the previous slide, but that you also can hear the vocals more loudly than the bass line. This is because the bass line was being filtered out by the high pass filter, while the vocals were able to pass through the filter and experience the amplification of the op amp. It is a little quieter than you might expect. This is because it hasn't been amplified by the crossover circuit.